Oh, I think, yeah.
I need to check. No.
If they see or another 7 minutes.
Yeah.
So we're waiting for we wait until 11:15 and then we will just go on.
Yeah. Mhm.
Well, it's a very special day. It's a special day, I think, for all of us. Listening, I don't need it. You can set it up for yourself. Was just a September. That's when Anand came into my office to discuss the possibility of joining the group, and I tried my best to steer him away from my group to move him to theory, because Anand was a theorist by DNA at the time, and somehow he's done some DNA engineering over the past 6 years, and he's become an experimentalist. Moreover, a material synthetic chemist, which was not at all in your DNA back then. But he's tackled a very challenging problem for us, which is this non-radiative relaxation in colloidal quantum dots. That might sound very esoteric, but the fact is, if colloidal quantum dots are ever useful, it's because they emit light. And when we started in the group working on quantum dots, we solved the problem with visible quantum dots using the core shell approach. And now people make beautiful emitting core shell quantum dots. And when Anand joined the group, it seemed that his work was going to be very simple. Just make me a bright quantum dot in the infrared. And he's gone a long way to that. And it's still extremely difficult. He achieved the world record of emitting quantum dots at 5-micron wavelength. And it's only 2%. So 2% fluorescence quantum efficiency sounds terrible. 2% by any measure is bad. You want 100%. But he's able to get something which is so far a world record, and we still don't know if that's the limit. And so in the next 6 years, Anand is going to stay here and continue. No, but anyway, so this is what a little bit the story that Anand is going to tell us, why it is hard, what he's achieved, the techniques, the approaches that he's, the minutiae involved in making this work, and I think someone else is going to take it from you in the next 6 years. So,
thank you, Philippe. Thank you, everyone, for coming, and thank you, everyone on Zoom, for attending virtually. So today, I'm going to talk to you about my work, my PhD work on understanding the non-radiative mechanisms and developing the synthesis of bright infrared quantum dots. So I'll first start by talking about what are quantum dots. So quantum dots are nanoparticles made of semiconductor material, and they are around 5 nanometers, few nanometers in size. And what does few nanometers mean? So it'll be helpful to compare this to some real life object which everyone can relate to, and that's a COVID particle. So it's like 100 nanometers in size, and quantum dot is this tiny. So this really tells us what is the scale of the particles that we are working with. So quantum dots, nanoparticles, these sound cool, but why are they important? So quantum dots are important because of two main reasons. One is that they are extremely bright materials, and they can be used to generate any color. So the color of the quantum dot can be changed just by changing the size of the material. And because of that, they can be used, they have a very high color purity, and they can be used to generate any given desired color. And using this method, we can make high definition TVs using quantum dot materials. And the second biggest benefit, advantage of quantum dots is that they can be solution processed. So typical traditional semiconductors need to be fabricated by lithography methods like molecular beam epitaxy or chemical vapor deposition. And this fabrication method makes the material very expensive. But since quantum dots are like molecules, they can be dissolved in solution, and you can just make these inks of quantum dots and just dry them on any substrate, and you can make the material. And this greatly bring down the cost of the material. And this is why quantum dots can be used to make cost-effective electronics. So quantum dots have been well studied in the visible regions, but they have a lot of potential in the infrared wavelengths. And this is something that we are working on in our group, using quantum dots in the infrared wavelengths. There are two wavelength regions which have great technological potential. One is the mid-wave infrared around 5 microns, where human bodies and other warm objects emit. And you can use quantum dots to make thermal cameras. And the second wavelength region is the near infrared, which has applications in telecommunications and also for bioimaging, because living objects are more transparent in this wavelength region, and you can do a lot of imaging and answering biological questions. So despite this potential, quantum dots are not yet mature enough to be used in commercial applications in these wavelengths because their performance is very poor. And this is a slide that we will go through multiple times during the presentation. On the y-axis, we have the photoluminescence quantum yield, which is, I'll come to the definition later, but this tells us how efficient the material is at emitting light. And this horizontal line, this green line, tells us that the quantum efficiency is 100%. So this is a plot for the quantum yield of quantum dots at several different wavelengths. And on the y-axis, we have the wavelength, x-axis, we have the wave number. You can see that quantum dots are almost have 100% quantum yield in the visible and the near infrared wavelengths. But as you go into longer wavelengths, like the shortwave infrared and the midwave infrared, the quantum yield drops really quickly. Especially at 5 microns, the quantum yield is just a few times 10 to the minus 4. So this tells us that there is a lot that can be done to improve the properties of quantum dots in these wavelength regions. And also this brings about the question, what is the reason for this exponentially decreasing trend of the quantum yield? And can we do something to overcome this? So this is the theme of my PhD research, to understand what is the mechanism for this relaxation. And I will be focusing on 2 wavelength regions. The first wavelength region is the midwave infrared at 5 microns, and the second is the shortwave infrared at 1.7 microns. And in the first part of my talk, I'll be focusing on the midwave infrared. So why do we care about quantum dots in the midwave infrared? In our group, we are using quantum dots to make thermal cameras. Every year, more than 1 million people die on road accidents, and 95% of these accidents are due to human error. Self-driving cars can give a solution to this pressing problem, but unfortunately, they are not yet safe to completely replace human drivers. If we include thermal cameras in self-driving cars, this can make them safer. And this is because of 2 main reasons. One is that the wavelength region in which thermal cameras operate, around 5 microns, 10 microns, is much longer than the visible region. So the scattering is much less. So even if it's a rainy or a hazy day, the car can still be able to see. And second, these cameras directly capture the light from warm objects. So even if it's pitch dark, you can see humans and cars using the thermal camera. So why are thermal cameras not being used? This is because they're extremely expensive. A high-speed, high-resolution thermal camera easily costs more than $50,000. And this is because the material that needs to be used to fabricate the cameras, mercury cadmium telluride, needs to be fabricated by expensive molecular beam epitaxy and wafer bonding, which is the main reason these cameras are expensive. So in our group, we are developing thermal cameras by using quantum dots. So we are using the same material that we use for the commercial cameras, but we are processing them in solution. And this solution processing makes the cost of the material much less. And by doing this, in the future, we can have a world where thermal cameras are used in self-driving cars and several other consumer applications where it was not possible before. The biggest bottleneck for bringing the quantum dots to commercialization is that they need to be cooled to very low temperatures for getting a good sensitivity. So on this graph, we have the detectivity D star for mercury telluride quantum dots as a function of temperature. And mercury telluride is the most common quantum dot material used for thermal imaging. The detectivity is a measure of the signal to noise ratio for the camera, and this tells us how sensitive the camera is. For quantum dot thermal cameras to be comparable to commercial cameras, the detectivity should be around 10 to the 10, which is this horizontal red line. And the ideal detectivity goal is called background limited detection, which is this blue line near 10 to the 11. Currently, we can achieve background limited detection around 120 kelvins. But this is not an option for commercial cameras because this cooling requirement makes them bulky and expensive. The dream is to achieve background limited detection near room temperature. So this exponential trend decrease is because the noise increases at higher temperature due to thermal recombination. So we need some way to reduce this noise without cooling the detectors. And we can do this by slowing the non-radiative rate. So in the next slides, I will talk about what non-radiative relaxation is. But for this slide, we can see that the detectivity goes as a square root of the non-radiative lifetime or a square root of the fluorescence quantum yield. The current mercury telluride quantum dots have a non-radiative lifetime of the order of hundreds of picoseconds, which corresponds to quantum yields of few times 10 to the minus 4. So for us to reach our dream, we need to find a way to reduce the non-radiative rate by 4 orders of magnitude. So in this slide, I will talk to you about what do we mean by non-radiative relaxation. So here I have a cartoon of a quantum dot, and here I have an electron microscopy image of what a quantum dot looks like. So when a quantum dot absorbs a photon, an electron and a hole are created, and this electron can relax back to the ground state and emit a photon of light, and that is called radiative relaxation. Or it can relax to the ground state and emit heat and relax by other mechanisms, which is called non-radiative relaxation. The fluorescence quantum yield is a ratio of the radiative rate to the total relaxation rate. So now this is just a formula, but what does this physically mean? The fluorescence quantum yield tells us if a quantum dot absorbs 1 photon, how many photons does it emit? So this tells us how efficient the material is at emitting light. And the point that we want to remember is that the non-radiative rate is directly related to the performance of the detectors. And our goal is to find the mechanism and find ways to slow the relaxation. So in this slide, I will talk to you about 3 common relaxation mechanisms for quantum dots. In this cartoon, I have these squigglies on the top, which are organic ligands, which are molecules which are bound to the quantum dot surface to stabilize them. In the first relaxation mechanism, which is called surface trapping, there are defect states on the surface of the quantum dot to which the electron or the hole will get trapped, after which it relaxes back to the ground state non-radiatively. For quantum dots emitting in visible and near-infrared wavelengths, surface trapping is the dominant mechanism. The remaining 2 mechanisms are more common for quantum dots in the infrared wavelengths. The second mechanism is called FRET to ligands. In this mechanism, the quantum dot relaxes to the ground state and transfers its energy to vibrations, to absorption of the ligand vibrations by a Foster resonance energy transfer. So Foster resonance energy transfer is a common energy transfer mechanism in which you have a donor and an emitter, and when they're really close together, the rate of energy transfer strongly depends on the separation. And this FRET to ligands becomes important as you go into the infrared because the absorption of the ligands starts to become stronger. And the third mechanism is unique to quantum dots emitting in the mid-infrared. This mechanism is called multiphonon relaxation. The phonons are vibrations of the crystal lattice of the quantum dot. And in this mechanism, the quantum dot relaxes to the ground state and excites a high order phonon process. So the quantum dot relaxes and creates around 10 to 15 phonons. Over here, it is important to emphasize that among these 3 mechanisms, the first 2 can be overcome by engineering the surface of the quantum dot, either by removing these defect states or by changing the ligands. But phonon relaxation is intrinsic to the quantum dot material, and there can be nothing that can be done to overcome this. So we have an important question here. What is the rate for multiphonon relaxation in quantum dots, and how does this compare to the relaxation rates that we currently see in our detector materials? Mercury telluride quantum dots have relaxation rates of the order of few hundred picoseconds. There have been theoretical calculations, semi-classical calculations, which predict that the phonon relaxation rate should be quite fast, faster than around a nanosecond. But there are other quantum mechanical calculations which predict that the phonon relaxation rate should be slower than microseconds. So this is a really important question, whether phonon relaxation is really as fast as a nanosecond. Because if it is, then it tells us that our quantum dots, the relaxation rate is only 10 times faster than the fundamental limit. And this tells us that we cannot improve the performance of the detectors much more than we currently have. So the goal of my project is to determine what is the relaxation mechanism and find whether phonon relaxation is indeed a major limitation for the quantum dot thermal cameras. So in order to do this, we have designed the growth of a thick shell around our quantum dots. When we grow a shell, which is of a type 1 band alignment, we are isolating the electron and the hole to the core of the quantum dot and separating it from the surface. And here I have a graph of the calculated PL quantum yields for core shell quantum dot with different shell thicknesses. And since the three mechanisms comes from fundamentally different physical origins, growth of the shell has different effects on the non-radiative rates. For the first mechanism, which is surface trapping, it involves a quantum mechanical coupling between the electron or the hole wave function to the defect states on the surface. So as we grow a shell, we are introducing a quantum mechanical barrier. So we should expect the quantum yield to increase exponentially with the shell thickness. The second mechanism, which is FRET to ligands, involves a fourth power dependence between the distance of the quantum dots from the ligand shell. So as we grow this thick shell, we should expect the quantum yield to increase as a fourth power of the total nanoparticle radius. And the third mechanism is multiphonon relaxation. And this is something that is intrinsic to the core. So even if we grow a shell, it will not do anything to change the phonon relaxation rate. So we should expect the quantum yield to be independent of the shell thickness. So looking at these three trends, we have an elegant method to determine the relaxation mechanism. So what we need to do is grow shells of different thicknesses, compare our experimental trend to these three simulations, and this will tell us what the relaxation mechanism is. Growing a thick shell on quantum dots is not an easy task, and it is especially hard for mid-infrared quantum dots. We have used mercury selenide quantum dots as the material for mid-infrared emission. The mercury selenide is a semiconductor which has a zero band gap in the bulk. But as we make a quantum dot, we get the band gap to span throughout the infrared region. But as we make a quantum dot, we also get discrete states within the conduction band. And the transitions between these discrete states are called intraband transitions. Intraband transitions are superior emitters to interband transitions because the whole density of states is much less than for the interband transitions. So in order to make mercury selenide quantum dots, where the intraband transition lies in the mid-infrared, which is 5 microns or 2000 wave numbers, we have synthesized mercury selenide quantum dots with a diameter of around 5 nanometers. And one important point I want to mention here, since usually in semiconductors, the valence band is full and the conduction band is empty, we do not observe intraband transitions. So in order for us to see these intraband transitions, we need to find a way to put electrons into the conduction band. So we need to negatively dope the quantum dots. And so now that we have the core material, our next step is to decide what is the material for growing the shell. The most important property of the shell is that it should have a type 1 band alignment, which means that the conduction band of the shell should be higher than the conduction band of the core, and the valence band of the shell should be lower than the valence band of the core. A second requirement that we have synthetically is that the crystal structure of the shell should be the same as the crystal structure of the core, and the lattice constant of the shell and the core should be similar to minimize strain between the two materials. The two shell candidate materials which satisfy these criteria and are easy to synthesize are cadmium sulfide and cadmium selenide. And we have decided to grow a cadmium sulfide shell as the synthesis is easier than a cadmium selenide. Previous attempts to grow a cadmium to grow a shell on mercury selenide quantum dots have only succeeded in growing a very thin shell. So the goal of my project was to find ways to grow a thick cadmium sulfide shell around mercury selenide quantum dots. And as I mentioned before, growing a thick shell is synthetically a difficult task, especially on narrow bandgap semiconductors like mercury selenide. And through our work, we found that the most important criteria for growing a thick shell is the growth temperature. If the growth temperature is too low, then we observe independent nucleation of the shell precursor in the solution, and they will not grow on the core materials. And if the growth temperature is too low, we also see a faceted growth or an irregular shell morphology. But if the temperature is too high, then we see alloying between the core and the shell, and this will lead to changes in the optical properties of the core, all of which we want to avoid. So in order to decide a shell growth temperature which is high enough that we do not observe homogeneous nucleation or and we get a spherical growth while we avoid alloying at the core shell interface, we have decided to grow the shell at 220 degrees. So in this slide, I have the synthetic details, and the details are not very important. But one thing I want to briefly mention is that mercury selenide quantum dots have a poor thermal stability. And before we grow the thicker shell at 220 degrees, it is necessary to grow a thin interfacial shell at a low temperature, which imparts thermal stability before the thicker shell is grown at a higher temperature. And using this method, we were able to grow a thick and roughly spherical shell up to a final size of around 1920 nanometers. And the XRD spectra show that the crystal structure of the shell grows mainly along the crystal structure of the core, which is a zinc blende crystal structure. So now that we have the synthesis, we have a second step that we need to do before we can measure the quantum yields. As we saw before, we need to dope the quantum dots for us to observe these intraband transitions. Right after synthesis, the quantum dots are intrinsic and they don't have electrons in the conduction band. So we need to find a way to put electrons into the conduction band for us to observe this intraband transition at 2000 wave numbers. Usually when we talk about doping, we think about putting foreign atoms into a material to introduce defect states. But another common way to dope quantum dots, which is much more convenient, is by changing the surface dipole moment. And this is the mechanism that we are using for doping our quantum dots. And in the next slide, I will go into the mechanism by which changing the surface dipole moment will dope the quantum dots. So here I have a cartoon of a quantum dot, and we have the valence band is full and the conduction band is empty. And we have the chemical potential is below the conduction band state. When we treat our quantum dots with cadmium acetate, cadmium ions like to bind strongly to the quantum dot surface. So we see a layer of cadmium ions on the quantum dot surface, and a layer of negative acetate ions will be in the solution as counter ions. This geometry leads to an electric field that is pointing towards the center of the quantum dot. And the electric field that is produced by this geometry will bring down the energy levels of the quantum dot states, so that if the electric field is high enough, then the conduction band state can go below the environmental chemical potential, and we observe a filling of the conduction band. And this is a very convenient way to dope the quantum dots, because just by changing the amount of cadmium acetate, we can obtain quantum dots with any given value of doping. While the initial quantum dots are undoped, which is seen by this blue curve, where we see almost no intraband absorption and a large interband absorption. As we increase the amount of cadmium acetate, we see that the intraband absorption increases and the interband absorption decreases. If we plot the value of intraband absorption versus interband absorption for all of these samples, we see this clear linear trend. And for any given unknown sample, if we put the position on this plot, this will tell us what is the value of doping of that sample. So now that we have the synthesis of the thick shell and we have a way to dope the quantum dots, we have measured the quantum yield of the quantum dots as a function of shell thickness. So here, this is a graph where the quantum yields are measured in an integrating sphere. So these are absolute quantum yield measurements. And this asterisk is to mention that these quantum yields were measured at low values of doping, because this is the value at which the quantum dots are the brightest. We can see that growth of the thick shell leads to a drastic increase in the quantum yield. While the initial cores have a quantum yield of few times 10 to the minus 4, the thickest shells have a quantum yield of 2%. Now, as Philippe said, 2% does not seem like a lot, but at 5 micron wavelength, this is the brightest reported quantum dot for any solution-based material. We have also done lifetime measurements in collaboration with Chris. And this, we see an increase in the intraband lifetime, which further confirms that the increase in the quantum yield is due to a slowing of the non-radiative rate. And finally, by comparing the experimental trend to the 3 simulations, we see that the experimental data matches fairly well with the ligand fret mechanism. But more importantly, the fact that we see this increase tells us that phonon relaxation was not the bottleneck for our core quantum dots. So this tells us that if we want to make more sensitive thermal cameras at room temperature, we need to find a way to slow this ligand fret mechanism. So this was the first part of my talk. I will now go to the second part of my work, which is to determine the relaxation mechanism in the shortwave infrared. So why do we care about quantum dots in the shortwave infrared? Quantum dots, biological tissue is much more transparent in the shortwave and the near infrared than in the visible. Just like how we use red light at stop signs because it scatters much less than green light. Similarly, by using longer wavelength of light, the scattering into tissue is much less. As we can see in this figure, using fluorophores in the shortwave infrared, we can penetrate much deeper into this mouse tissue. The Hongji Dai group at Stanford have calculated what is the penetration depth for light of different wavelengths as a function, what is the penetration depth for infrared light at different wavelengths. And we can see that there is an increase as we go to longer wavelengths because the scattering is much less. But there is also a compromise as we go to longer wavelengths. The absorption by water also strongly increases. The wavelength region where there is a compromise between the scattering and the absorption is the shortwave infrared between 1.3 and 1.7 microns. And 1.7 micron is the wavelength at which tissue has the greatest penetration. The Hongji Dai's group have used quantum dots emitting at 1.7 microns to do live imaging within the brain tissue, and they can achieve a penetration depth of 1 to 2 millimeters. But the biggest challenge of the current quantum dots emitting at 1.7 microns is that their quantum yield is extremely low. It is only 2%. So if we can get brighter quantum dots, say 100%, this will more than double the penetration depth that is possible, and this can answer a lot of biological questions which were not possible before. Before I go into how to make brighter quantum dots, I want to bring the question of why are we not considering using organic molecules for deep tissue imaging? So here I have a graph of the quantum yield for organic molecules, including dyes and fluorescent proteins at different wavelengths. So we can see that as we go to longer wavelengths, the quantum yield decreases exponentially. And especially in the shortwave infrared, the quantum yield is extremely poor. This decreasing trend is called the energy gap law. So energy gap law is because as we go to longer wavelengths, the energy of the organic molecule emission becomes closer to the vibrational frequency of the molecules, and this leads to a very fast non-radiative relaxation. But on the same plot, if we put the quantum yields of quantum dots, we can see that quantum dots are around 100 times brighter than these organic molecules. So even though quantum dots have a disadvantage of having a larger size and having issues of toxicity, in the shortwave infrared, there is no other material. But these are quantum dots that are solubilized in organic solvents. So for doing in vivo imaging, we want to solubilize these quantum dots in water. And here I have plotted the quantum yields of quantum dots solubilized in water as at different wavelengths. And we can see that we have a similar trend as the quantum dots in nonpolar solvents, but the quantum yields are around 5% lower, 5 times lower. And I want to emphasize that these are materials, these are quantum yields for several different materials, including lead sulfide and indium arsenide. So this tells us that there is some universal trend which is resulting in this low quantum yield as we go to longer wavelengths. And this is something that hasn't been discussed or explained before. So motivated by our previous work on the fact that ligand FRET is the dominant relaxation for quantum dots at 5 microns, we have calculated what is the rate of FRET between the quantum dot and the ligands, as well as quantum dots to solvent molecules. So the calculations are these solid lines, and we can see that the calculated trend matches fairly well for both the organic molecule, organic capped quantum dots, as well as quantum dots solubilized in water. So if you want to make brighter quantum dots, the solution is clear. We need to find a way to slow this FRET to water molecules. So we need to grow a thick shell around the quantum dots. And we have done this at 1.7 microns, which is the wavelength at which a tissue is the most transparent. Before I go into our synthesis, I want to talk about why mercury selenide quantum dots would be superior to the currently used quantum dots for in vivo imaging. The current used materials are lead sulfide based quantum dots. And as you can see from this band structure, the conduction band of the cadmium sulfide shell is quite close to the conduction band of the lead sulfide core. So as we grow a shell, there is going to be a finite electron density in the shell, and this leads to a reduced efficiency of the emission. So it is observed that as you grow a thicker shell, you do not observe an increase of the quantum yield. And this is not just true for lead sulfide, but also for other shortwave infrared materials like lead selenide and indium arsenide. All of them have a quasi type 2 band alignment, and we don't see an increase in the quantum yield as a function of shell thickness. But from our knowledge, the only materials which have a strict type 1 band alignment are the mercury chalcogenides. So mercury sulfide, mercury selenide, and mercury telluride. So although they have the issue of toxicity, there is no other material which has this band alignment, and this is the only way right now to get brighter materials in the shortwave infrared. So so this was our motivation for growing a thick cadmium selenide shell around mercury selenide quantum dots for slowing the non-radiative rate in the shortwave infrared. So similar to our previous work, the first step is to grow a thin interfacial shell to impart thermal stability before we can grow a thicker shell at a higher temperature. And using this method, we were able to grow thick and roughly spherical shells. And as we can see from the absorption and emission spectra, the peak positions do not change with the shell thickness. And this is a further confirmation of the type 1 band alignment between mercury selenide and cadmium selenide. One very convenient fact about mercury selenide is that the same material can be used to get mid-infrared emission as well as shortwave infrared emission. So for the same quantum dots, which have a diameter of 5 nanometers, if you dope them, we get the intraband transition at 5 microns. But if they are undoped, you get the interband transition at 1.7 microns. So after the synthesis, we have measured the quantum yield as a function of shell thickness. So the y-axis is the quantum yield for mercury selenide, cadmium selenide quantum dots with different diameters. The black points are absolute quantum yield measured in an integrating sphere. The red are lifetimes measured in collaboration with Rich Schaller at Argonne. And the black dotted line is the ligand FRET calculation between our core quantum dot and the Euler lemon ligands. We can clearly see that all of these three trends match quite well. And this is a further confirmation that the ligand FRET is not just dominant in the midwave, but also in the shortwave infrared. When we plot our quantum yields with the reported dots, we see that the quantum yields are much brighter than the previous materials. And while the previous brightest materials were emitting at a quantum yield of 20%, our quantum dots have a quantum yield of 60%. But the fact that we see an agreement of our theoretical trend with the data tells us that 60% is not just the end. And if we have a way to grow a thicker shell, this could, in principle, reach 100%. And while our initial motivation was to slow the non-radiative rate for quantum dots in non-polar solvents as well as in water, we have calculated what would be the rate of non-radiative decay from the quantum dots to water molecules for our 30-nanometer quantum dots. And we see that the quantum yield is 12%. And this 12% is 6 times brighter than the previous reported quantum dots. And overall, our work shows that in order to obtain bright fluorophores emitting at 1.7 microns, it is necessary to grow a thick shell. And by synthetic strategies where we can grow a thicker shell, we can expect this quantum yield to reach much higher. And this has a lot of potential for bioimaging. So I want to end by summarizing what I have discussed till now. We started by this trend of decreasing quantum yield as we go to longer wavelengths. And the fact that mid-infrared quantum dots have a lot of potential for thermal imaging, but their quantum yield is extremely low right now. So in order to determine the relaxation mechanism and slow the rate, we have calculated the rate of fret between the quantum dot and ligand molecules, as well as the quantum dot to solvent molecules. And we have found some universal strategies for growing a thick shell around mercury-based quantum dots. And by growing this shell, we have gotten a record quantum yield of 2% at 5 microns and 60% at 1.7 microns. So this 2% is extremely low, and there is still a big room for improvement. So after 6 years, where with Philip, next PhD student, if we can just extend this to 100%, then we will get thermal cameras which are sensitive at room temperature and will have a lot of commercial applications. So I want to discuss one slide on some future directions that are possible. Our growth of robust shells around mercury selenide quantum dots can be used to make bright LEDs. And this is something that we are doing in our group right now. An eventual ultimate goal is to completely replace the organic ligands and put the quantum dots in an inorganic matrix so that there is no infrared absorption. And this is something which hopefully the next student will do. But this will be the way to get sensitive thermal cameras which have a slow non-radiative decay. And the second scope of my work for in vivo imaging, we are currently pursuing a collaboration with a group in Stanford for using our quantum dots for in vivo imaging. And another medium-term direction of research could be using these near-infrared quantum dots, not just as fluorophores, but also as biosensors by using a fret-based mechanism, which can be used for sensing biomolecules deep in vivo. So I want to end my talk by spending a few minutes to thank everyone who has contributed during my PhD. So I want to thank my advisor, Philippe. It has been a great learning experience in the group, and I'm really grateful for the opportunity to work in the group. I want to thank all my group members, Professor Rich Schaller and Aritrijit for helping me with the measurements. And I want to thank our funding agencies for making sure that I could get food and shelter during my PhD. I want to thank my family. First, I want to thank my father, without whom none of this would have been possible. It was due to his relentless encouragement for me to pursue my what I really like. And if it was not for his support, I wouldn't have pursued a career in science. And I want to thank my mother for her endless support during my difficult times, and my brother and sister-in-law for their support. And I want to thank Meera auntie, who is not officially a family, but I consider her family, and she has been there for me during my most difficult times. I want to thank my grandmother, Chai Pachi, who came all the way from India to attend my thesis defense and my convocation. And I want to thank my family in the US who have made me feel at home, even though I'm so far away from India. my family in New Jersey, Sandesh Bappa and Shantaka's family, Pratibha Mai's family in New York, Amit Anna's family in South Carolina, and Vidya Mami's family in South Carolina, and Aditi Pachi's family in Atlanta. So during my time in Chicago, I have made unlimited friends, and I cannot put all of the names over here, but I put some pictures whose pictures I could find in my Google Photos page. I want to thank my Urbana-Champaign friend group, Anua, Sarthak, Isha, Srijani, and Amrita, my roommate Aritrajit, Agnish, Manish, Pranjal, Lavanya, my board game group, Sam, Michael, and Ram, and my undergrad friends, Sridevi, Shriya, Naren, Shubayan, Alistair, and Arpan. And I want to thank Ram's cats, Maya and Kalu, who are just the most adorable creatures. And many of you might know that I'm transitioning to pursue a postdoc in neuroscience. And it has been a difficult journey, but it wouldn't have been possible without the support and encouragement from all my friends. So I have a few of them here. There's Claire, Matt Ackerman, Kim, Tomojit, Xuanwang Yang, James, Melina, Fauzia, Nabila and Pooja, and Chaitra. And finally, I want to thank all my mentors. I want to thank Anish Vettil, who was the main inspiration for me to pursue this postdoc transition. And he picked me up during the most difficult period of my PhD and inspired me and motivated me to pursue a career direction which I really find exciting and fulfilling. And I want to thank Bojit Yan, who is my God professor and who has given me the unlimited support and encouragement and all the resources that I need for pursuing my career ambitions. And all my other mentors who have given me support, encouragement, and recommendations for my fellowship applications: Mike Tessel, Vera, Amanda Young, Aaron Dinner, Alison Squire, Dimitri Talapin, and my mentors in India, Professor Ramakrishnan, Anshu Pandey, and Gautam Bharali. And I want to thank you all for your attention, and I'll be happy to answer any questions.
Thank you very much, Al. This was a whirlwind, and you glossed over all the little minutiae, all the little details. Those are the ones, of course, that make this truly special. The floor is open for questions from the audience first. Yes. Yeah, no, great talk.
Thank you.
Like experience of like how you like what's involved in the simulations you perform to calculate the
I have backup slide for that. So this is our thread calculation. So we have, let me put that there. So we have, this is the formula for FRED between an absorber and an emitter. We have the absorption from either the ligands or the solvent, which we have measured experimentally. And we have the emission spectrum of the quantum dots. So we fit that to a Gaussian and plug this into an integral to do an integral over the frequency. And we have the ligand shell starting from the quantum dot surface to around 1 nanometer. So for the ligand FRET, we do this radial integral from the surface to the ligand end. And for FRET to water, we do the integral from the end of the ligand shell up to infinity. And so that will give us the non-radiative rate, and the quantum yield is calculated. We use it. The quantum. Yeah, so the quantum yield is found by a ratio of the radiative to non-radiative rate by that formula.
The question had also some, you were asking also about the traffic and the relaxation. How exactly how precise?
Yeah, it's a simple model, but it matches the experimental data quite well.
You're basically treating photoresist.
Yeah.
Questions? Yes.
Summary slide on it.
Uh-huh.
So yeah, on this graph, is this decay intrinsic? So, or do you imagine that you can make your big star? Is 100% achievable, or is this like more fundamental?
So this trend is because the ligands are strongly absorbing at this region, and by growing this shell, we are separating the core from the ligands, and we are slowing that relaxation rate. To go brighter, either you need to grow a really thick shell, or you completely remove these absorbing ligands and put something else, like some inorganic ions or inorganic matrix, and that will slow the rate. But we need to find some way to slow the fret. So it's not intrinsic to the quantum dot material, but intrinsic to the environment around it. Yeah. 21. So okay, so the question is, what is the reason for the discrepancy, and can we go brighter if we go to thicker shells, right? So one thing I did not mention, this star, small star that we see over here, I didn't mention that we see if the doping is large, then we see that the quantum yield decreases significantly as we go to larger dopings. So there is another mechanism, which is not just the ligand fret, but probably due to defects within the shell, which is reducing the quantum yield. So this disagreement could be because of that. It might also be due to the fact that our shells are not entirely spherical. Where is that? Yeah, so it's like it's not a very precise model. So, but we believe that if the problem of the defects is solved, then you should be able to go to brighter quantum dots if you go thicker shell. Yeah. Aditya?
And of the formally theorists speaking, deeply shared that optimism. Speak up, please.
So you mentioned there's absolutely no effect of the shell, but even though if you have like an anesthetic of the shell, if there really no effect of even a thick shell, I would assume the picture will somehow by some signal of form affecting the
Okay, you have a good point. So this is, I guess my graph is next. So you're right, it's a simplistic argument. It depends on what phonon modes are involved. If it is the bulk phonon modes, then yeah, the strain can change the phonon frequency and it will change the rate. But also, if the phonons that are involved are the surface phonon modes, then those there can be an effect. So if you're asking why we feel it's not phonon relaxation, the frequency dependence of phonon relaxation, like we see this exponential decrease of the quantum yield because of ligand absorption, that length scale will be around 1500 wave numbers, which is the CH stretch. But if phonon relaxation is the dominant relaxation, then that scale should be the phonon frequency, around 50 wave numbers. So we'll see a very strong dependence of the quantum yield on the frequency of the excitation. And that's something we don't see experimentally. But also, if it's limited by phonon relaxation, then we will see a very strong temperature dependence. And when we cool our quantum dots, we do not see that too. So those are like two reasons why we feel it's not phonon relaxation. Yeah.
Thank you for the talk. Question: I was curious about the effect of temperature on these three contributions. Like if you cool the samples down, I know the bodies have room temperature operation eventually, but let's say you cool it down, how will these three components vary?
Okay, yeah. So the question is, what are the temperature dependence for these three mechanisms? I don't have a slide, it's on my thesis. The ligand fret just depends on the absorption of the ligands. So we do not expect to see any temperature dependence, so it should be flat. Trapping is usually there is an activated, it's an activated dependence. So we should see an Arrhenius type dependence, Arrhenius type exponential behavior. And phonon relaxation will, when the phonon frequency is quite low, you will expect the temperature dependence to be temperature raised to the number of phonon modes. So T raised to 15 or T raised to 10. So I don't have a graph, but all this exponential trend and that T raised to 15 trend, this is much stronger dependence than the trapping. So that's another way where we can distinguish the mechanisms.
And you want to emphasize that you see no temperature dependence.
Yeah, we don't see temperature dependence.
It doesn't get better. Otherwise, we would have blamed that. Yes.
Yeah, 2.5, it's hard to say. Not significant. Yeah.
Okay, so I don't know if everybody will be waiting outside after the deliberation of the committee, but I think you mentioned that you had a reception at 4 p.m.
Or yeah,
So
outside
if
here.
something else happened, and I will inform you, but otherwise, we will see you later this afternoon. I think same room, right?
Yeah, the Kent 114, just outside
Thank
here.
you all for coming. It's amazing to see this kind of attendance for these defenses. Not something I'm going to do. Thank you all.